method, we were trying to draw sample from some distribution, target distribution. The distribution is intractable. We know it only up to a normalizing constant, and the objective in sampling method was or is to draw samples that are representative of the distribution. The challenge here is that these methods are generally expensive. So if you, when you do homework 2 or practical 2, you will realize that these methods are expensive because samples get rejected, sampling is slow, and so on and so forth. Obviously, sampling is easily parallelizable. I mean, it is embarrassingly parallelizable, so that's not a problem, but still it is slow. And so the other method is the approximate inference algorithm, which we will start on Monday, where it is very fast, but there you will not get some exact distribution. You will assume some distribution and try to fit it to the, or make it as close as possible to the target. And that we will start in the next lecture. Now, before completing the discussion on sampling based approach, I want to discuss 2 algorithms to wrap it up. Now, these 2 algorithms, it's not like I have already covered everything in sampling and there are only 2 left. It's not like that. There are many other algorithms that I am not covering. I am only covering the ones that are the most popular ones, and also those are kind of the foundation for any other sampling based algorithm, which you can learn on your own if you know these algorithms. These are kind of the most fundamental one and also the most useful or most widely used. I mean, these are the ones that are the most popular ones. So today we will try to talk about 2. We will go into details of Hamiltonian Monte Carlo. Sequential Monte Carlo, how much I can cover depends on how much time is left after I am done with Hamiltonian Monte Carlo. But at the very least, I will give you some idea about sequential Monte Carlo, because in your homework 2, there is one question on Hamiltonian and one question on sequential. So both of these are part of your homework 2. And it is okay to not cover sequential Monte Carlo in details, because it is basically applying importance sampling and metropolis testing again and again. So because you know both of this, so you have the foundation for sequential Monte Carlo already. The only thing that is different in sequential Monte Carlo is that you have to apply those 2 things again and again sequentially, and that's why the name sequential. But Hamiltonian, again, it's basically a modified version of metropolis testing algorithm, but there are some fundamental concepts that are there in Hamiltonian Monte Carlo which is different from metropolis testing, the way we know it. Okay. So with that background, let us start. These are the same slides, so I'm not going to talk about those, and I'm directly going to jump into Hamiltonian Monte Carlo. Okay. So we are going to talk about Hamiltonian Monte Carlo, but before that, let us quickly recap metropolis testing, because Hamiltonian Monte Carlo is a type of metropolis testing algorithm. Okay. So in metropolis testing, what was the idea? The idea was that there is a proposal that you will select, and in metropolis testing it is kind of generic. There is no symmetric condition or all those things. So you sample from the proposal, and then you either accept it or you retain the previous sample. You do not reject based on certain acceptance ratio, right?
I have a question. Sir, why do we retain that sample?
Markov chain. Okay.
So we want to accept.
Yeah, it's the Markov chain Monte Carlo, right? So that's why. So now, what we want to do is that, so that is the basic idea of metropolis testing. Now, I told you last time that metropolis testing is one of the top 10 algorithms of the last decade, of the 20th century, not decade, last century. But I also said that there are still people are still coming up with variants of metropolis testing algorithm. So what do you think is there that needs modification or improvement in the metropolis testing algorithm? What do you think you can improve upon? Because in metropolis algorithm, the limitation was that you need symmetric proposal. That has been addressed in 1970 by Hastings. So in metropolis testing, that limitation is no longer there. But people are still developing variants of metropolis testing. So what do you think is the limitation that people are trying to address, or what do you think is the component that people are trying to improve upon? So what do you think it is in metropolis testing? Try to remember the algorithm and then see if you can come up with an answer. What do you think needs improvement in metropolis testing? That anyways does not matter, apart from the fact that a burn-in period, but that has minimum to no effect. So starting from initial sample does not really have much influence. But for metropolis testing, what are the three conditions we need to satisfy? Detailed balance or reversibility, irreducibility, and aperiodicity. Now there, if you look into detailed balance, the kernel is the important thing, right? To design a kernel is the main thing of metropolis testing or any Markov chain algorithm. To design the kernel K. And how do you design the kernel K? By selecting a suitable proposal. That is the only way to improve the kernel. Because the kernel is what? Proposal times acceptance plus integration of proposal times rejection and then integration, right? So if you have to improve that kernel, the only thing that you can improve upon is the proposal. And that is what people have been working on even now. Like one algorithm I said was HMC, where they try to build a neural network as a proposal. Generative model, GAN, as a proposal for MCMC, for metropolis testing. So that is known as HMC. That is one algorithm. Okay. So the point I'm trying to make is that selecting suitable proposal is important in metropolis testing, right? That is the point I was trying to make. Okay, it is very important to select a suitable proposal because with a suitable proposal you can make the algorithm more efficient. Okay, so now this brings us to the question that we have not discussed anything about proposal. All the derivation was based on a generic Q. I never told you what is a good proposal, what is a bad proposal. But I did mention that thumb rule is that acceptance ratio is between 0.28 to 0.4. That I did mention. So a good proposal is something that will probably satisfy it. But what is the most popular proposal is the random walk proposal in metropolis testing. Okay. So the most popular proposal is the random walk proposal. Where the idea is simple, that your next particle, the samples are known as particle by the way in all these methods, xt plus 1 is equal to your current particle plus some epsilon, where epsilon is from some zero mean Gaussian distribution. Okay. So this proposal, if you use, that is known as the random walk proposal. So what is qxt plus 1 given xt? It is Gaussian with mean xt and variance sigma square. So the proposal, this basically boils down to the proposal q xt plus 1 given xt is equal to a Gaussian over xt plus 1 given xt is the mean and sigma square is the variance. So this is known as the random walk proposal. Okay. And this random walk proposal was, it is said, I don't know if it is true or not, but it is said that it was developed by watching a drunken person walk. So the idea is that you are at your current location. If you're drunken, you don't know where you will go. You can randomly go this side, that side. You can stay here also. So that's how it was developed. That's what it is said. Okay. So, but the idea is that given that you are in the current step, you can go to the next step with certain mean, and I mean the mean remains the same with certain variance, right? And if you remember when I started talking about the Metropolis algorithm, I initially said that this is a point, let us take a small Gaussian. So that is actually I was drawing this last to last lecture in Metropolis algorithm. Okay. So this is one of the most popular proposal, and this proposal actually follows the fact that xt plus 1 is dependent on xt. So the samples you are drawing are definitely not IIDs, and so on and so forth. Okay. Another proposal which is not so popular and for the right reasons is the independent proposal. The second proposal, this was one example. The second example I am giving you is of the independent proposal. What do you mean? What do you think independent proposal mean? Can someone guess? What is independent here? Correct. So qxt plus 1 given xt will now not depend on xt. So it will be equal to Gaussian with some mean and some variance, and that you can select. Okay. So in this case, your q xt plus 1 given xt is a Gaussian, and it may not be Gaussian also, by the way. It can be something else. I am taking Gaussian to satisfy the irreducibility criteria, but you can take something else with Gaussian minus infinite to infinite. Irreducibility is addressed. Okay. Previous case also it is Gaussian, so it is anyway satisfying. Even if I am placing a mean somewhere, taking a small sigma, theoretically it is minus infinite to infinite, satisfied. With some mean, which I don't know, and some variance. Okay. Now, can you remind me where have you seen such a proposal? Have you seen such a proposal somewhere? Rejection sampling, right? This kind of proposal you use in rejection sampling. It does not depend on the previous sample. You select some proposal that can be uniform, that can be Gaussian. So this independent proposal is basically the proposal that you use in rejection sampling. But what is the problem of this, and why do you think it is not popular? The reason is that this proposal is fixed. It will not change. As a result, the conditions that are there for rejection sampling have to be imposed on this proposal. For example, the tail should be fat, it should supersede the target, and all those things will come into picture, which was not there for random walk because the proposal was changing with t. Here the proposal is not changing with t, and as a result it should supersede. Okay. And since it should supersede, that means you have to be careful. It's restricting. Okay. So that's why the second one is not so popular. And at the end of the slide, you will get a MATLAB code with Metropolis testing algorithm done with both the proposal. Okay. But the bottom line from here is that proposal is very important. Designing a good proposal is very important. And that is what Hamiltonian Monte Carlo is. Hamiltonian Monte Carlo is a Metropolis testing algorithm where there is some inspiration taken from physics to build a good proposal. And the physics from where it is taken is Hamiltonian physics, Hamiltonian mechanics, and that's why the name Hamiltonian Monte Carlo. Okay, so that's the reason of the name. So HMC stands for Hamiltonian Monte Carlo, is a variant of Metropolis testing algorithm. HMC is a variant of Metropolis testing algorithm where the proposal is designed based on some inspiration from physics or mechanics. Okay. Okay. So to start with, you should always remember that Hamiltonian Monte Carlo is a type of metropolis testing algorithm. So is Gibbs sampling. Gibbs sampling is also a type of metropolis testing algorithm. Okay, you just have a proposal which is based on conditional there. Okay, and everything is accepted. Okay, so now to understand this, we have to again start from fundamental, because as some fundamental aspects. So when we are, suppose I have a distribution like this, right? So let's say I have a distribution like this. Okay, I took a Gaussian, it may be multimodal or something, does not change anything. Okay, so when I sample from it, remember that my x-axis is the sample, okay, and y-axis is the PDF. This is small x actually. So when I sample from it, what does it even mean? What does sampling mean from such a PDF? What does it mean? When I'm saying that I'm sampling from a Gaussian or sampling from a uniform or some beta or something, what does it mean? It means that you will select sample randomly, but the amount of sample you are taking in a zone is proportional to the amplitude or height of that zone. That means in this case, towards the middle you will have more samples, whereas as you go away from the middle, the mean, you will have less samples. That is what sampling means, right? And that's why I say that when that is followed, we say that the samples drawn follows this distribution. If it was uniform, no matter where you go, if you take small equal area, you are expected to get equal number of samples, right? So sampling here means that if I draw samples from here, if you get 5 samples from here, from this location you might get 2 symmetric, so 2, and from here you may get 1 sample. Okay, I mean, again, these numbers are arbitrary, just these arrows are there to kind of emphasize that at which location more samples are expected. So 5 is greater than 2, so more samples at the location where I have given 5 arrows. Okay, that is what sampling means. So what we do in Hamiltonian Monte Carlo, or the inspiration of Hamiltonian Monte Carlo, comes from flipping this distribution. So what we do is we flip this upside down. Okay, so if I flip it upside down, if I flip it upside down, it will look something like this, right? I've done nothing, I've just flipped it. Okay, and here you can think of a ball, right? Think of a ball that you are letting it roll from here, or some rain is, it is raining and then rainwater is going. You can imagine it like that. What will you observe? Where will you find the maximum water? At the bottom, right? You will find maximum water here. So here it's more like you let it go from here, and then you will find, if you start from anywhere, you will see that you are getting most of the things from at the bottom, right? And then occasionally if you give external force, it can get even at that. It's not like you will not get nothing at the top. If you give external force now and then, you will get samples at the top as well, right? So this is not exactly, but it is analogous to the energy landscape of the target distribution. This is more like energy, and if you think of particles wants to reside in the low energy state. In mechanics, if you think of the molecular state, the particles always want to reside in the low energy state. So if you look at this, it is more like the energy level, and most of the particles will try to stay at the bottom, which is the low energy level, right? So that is the first analogy. Okay, so this is basically minus probability. Okay, let's first write this. This is, let's say, pi of theta, right? Or yeah, pi of theta is fine. Okay, pi of theta or pi star of theta. Normalizing constant is not known, but let's say pi star of theta. Okay, this is minus pi star of theta And not only that, you can take a log also. We generally take log. When you say energy landscape, we take log. It makes our life easier, okay? Because log is a monotonously increasing function, right? So it's fine. It will not create any problem. And anyways, with log, in probability, we always work with log because it makes our life easier. So the energy landscape that we consider is minus negative log probability or negative log posterior, unnormalized, okay? Why I am calling it posterior? Because target is going to be my posterior. Target is the posterior from where I want to sample, probability of theta given d. And I have flipped it, and then I can draw the analogy with the energy, and I can say that this is kind of like the energy landscape, and most of the particles will like to stay in the bottom. So then I can use the energy landscape to sample, okay? And we'll go there in a while. So now, there is some inspiration from statistical mechanics as well, okay? And I already gave some reference that in low energy state, but let us discuss it in little bit more details, okay? So suppose I have this energy, okay? And let's say this is my E0, E1, E2, E3, okay? And it can go up to different energy level, E10, E100, En, okay? So each horizontal line is representing our energy level. The one at the bottom are the low energy level, the one at the top are the high energy level. Now if we have many particles, okay, molecular particles, I said just now that the particles wants to stay in the low energy level. So what do you expect you will see? If I plot it, what we will see is that more particles will be at the lower level, and as we go up, less particles will be observed. Some particles can be at E1, E2, E3, but it will the number of particles will reduce as we increase or go up in the energy level. Okay? So
what does energy represent in this graph?
What does energy represent in this graph? What does energy means what of a particle? What is energy of a particle or molecular thing? Any system, there are molecules moving around, right? Particles. If you look at the microscopic level or molecular level, you will see particles moving around here and there. What does energy means? For anything, in our case, energy will mean kinetic energy plus potential energy. Kinetic energy because it is moving, half mv square. Potential energy because of gravitation. That's all. That is what energy is, and we'll come to that in a short while. Okay. And Hamiltonian is summation of that. That's why Hamiltonian Monte Carlo. So as we said that maybe more number of particles will be here, relatively less number of particles here, even less number of particles here, and you can go on like that. Okay. So what do you think is the distribution of this particle or distribution of the energy? What is the distribution of the energy? Probability of E. It is decaying, right? And I will say it is exponentially decaying. That's a kind of decay. So exponential of minus EI. If I am looking at the ith level. So energy of the ith is equal proportional to exponential of minus EI. Okay. There will be some division which I am not writing right now. Okay. Now you can realize that if EI is small, or rather if EI increases, negative sign will reduce it, exponential will be less. So less number of particles will reside at the higher energy level. At lower energy level, this number will be higher. Okay. So now, what will happen, or what do you think will happen if you think that I provide temperature to that system from outside? So there are particles that are moving, I give temperature from outside. What will happen? Temperature is a form of energy, or temperature can generate heat, energy will come. Because of temperature, what happens is if I give temperature from outside, some of this particle may jump to the higher energy level because I am giving additional energy in form of temperature. So the particle will take that energy and move to the higher energy level. So what does it mean? That if energy is more, temperature is more, then more number of particles will stay in the higher energy level. So that's why it is also divided by T. So T is the constant. So that means the PDF looks something like this. That means here is the energy. The PDF will be something like this. If you increase T, it will be something like this. The decay rate will reduce. If you increase T, the decay rate will reduce because decay rate is 1 by T. Correct? Is the intuition clear? I will not say that is it clear because statistical mechanics is a course of its own. So I am not expecting you everything to be clear. But what I am expecting is that if the intuition is making sense or not. Because statistical mechanics ends here. Now we'll go back to the statistics. Repeat.
Can we say that if the curve is moving, like the temperature is increasing?
If you not temperature is not increasing.
Like the temperature is representing in that equation the randomness.
No. The particles are anyways random because particles are moving and they will be at different energy level. So if you provide temperature, then some particles will go up. As a result, the decay rate will reduce. Temperature is not random here. Temperature can be random. That's a mechanics part. Here, temperature is not random. Here, I am just trying to explain that if you give more temperature here is the external agent. If you give that external agent, it will go, the energy level will increase. That's all. Okay, that is all. Nothing else. Okay. Here, the important thing is the energy EI, and that's why you will realize that I have written EI, but I have not written TI. Because temperature is giving to the system as a whole. EI is part particle I am looking or part energy level I am looking at. Okay. So, okay. The take home message from here is that probability of EI is proportional to exponential of minus EI by T. And this is known as the Boltzmann's distribution, which is used in statistical mechanics, molecular dynamics. This is the Boltzmann distribution. Okay. So this is going to form the motivation for Hamiltonian Monte Carlo. Okay. To do that, we need to calculate the energy. And as she was asking, what is energy here? And I told already, so energy here is basically the combination of kinetic energy, which is coming because of the momentum or the velocity, and the potential energy which is coming because of gravity or the fact that it is at a position. Okay. So energy here is the basically I will denote it as H is equal to kinetic energy K plus potential energy U. And when I am saying kinetic plus potential, I am assuming that there is no, this is a conservative system. So there is no friction or something like that. Okay, Hamiltonians are generally for conservative system where energy is conserved. Okay, so that is the consideration here. Okay, now each particle here, remember that ultimately these particles are going to be samples that I want to draw. Ultimately, so that is the whenever I say particle, remember keep in your mind that is going to be a sample. But a question here is that how do you characterize a particle? For any particle, theta, let's say, or p, let's say, how do you characterize it? A particle is characterized by the position where it is, which is theta I. Theta is the position, okay, and that is also the particle, and the momentum it has. So a particle will be characterized by two things: the position and the momentum. Now kinetic energy will be a function of only the momentum because it is half mv square. So it is momentum square by 2 times mass. Okay, so the kinetic energy is a function of m and u is the function of theta. So let me write it here. A particle is characterized by theta I comma mi. Theta I is the position, this is the momentum. Okay. Okay. Now what is the kinetic energy of the system? What is the kinetic energy of the system? I just now said half mv square, which is equal to momentum is mv. So half m square v square divided by m. M is mass. Okay. But here m is momentum. So k of m is equal to mi square by 2 times mass summation over, or j rather I will say, j equal to 1 to d. So now can someone explain me what is d, or what is the index j indicating here?
Particles.
Number of dimension, because momentum, generally in physics sense we will have maximum 3 dimension, but in probability it can be 100 dimension also, because my particle may not be univariate, right? It can be multivariate. So if it is multivariate, it will have momentum in different directions, in each direction, one particle. That is what d is denoting. If you have to relate it with the physics, think about a 3D problem, there will be mx, my, mz. So that's what it is. For a ith particle, it will have momentum in x direction, y direction, z direction. That's what it is. Okay. And u here is the potential energy, and that is what I was drawing earlier. So this is what we will consider as u. Okay. Minus log of u of theta is equal to minus log of pi star theta. Okay. So now let me stop here and give you 2 explanations. So the explanation I am providing is from mechanics point of view till now. So I am trying to inspire this algorithm from mechanics. There is another way of explaining it, which is from the statistical point of view. And what happens is that when I explain from mechanics point of view, you will realize that kinetic energy is coming from mechanics, which is making sense. But why am I selecting u theta to be this case? One reason is obviously because I have reversed it and it looks like energy, but that's more of an intuition or an analogy, but that's not exactly energy. Correct? The other explanation comes from probabilistic point of view. And there what you do is that you assume that along with theta there is m, and you write the joint distribution. If you write the joint distribution of theta and m, what will you get? Probability of theta multiplied by probability of m given theta. And that theta, probability of theta is that u, the log of that, right? And m in given theta is your modeling constant, and that you will model yourself. So fundamentally what I am trying to say is that if you go from mechanics point of view, kinetic energy will make sense. The other part is more of a modeling and analogy based. Whereas if you go from statistical point of view, you will realize the second term is coming automatically, u theta. Whereas the first term is something you have to model and you can select it. And there are Hamiltonian Monte Carlo algorithm which has selected different forms of k. There are algorithms, okay? However, I am not aware of algorithms that have selected different form of u. Okay? So this is my Km and u theta. Km is the kinetic energy, u theta is the potential energy. So what is the total energy now? Summation of the two. By the way, to make things simple, so this is equal to, let's write m square by 2 mass, assuming d equal to 1. Okay, just to make our life simpler. I don't want to work with that summation. Okay. So now, What is the distribution of the energy? P of EI. What will I do to find that? How will I now find out P of EI? Simple, I will find out the total energy, which is summation of these two, and substitute it into that expression. Okay. There are two things that are unknown to me, T and M, but because from a statistical point of view I am doing, they don't matter. I am going to take M equal to 1, T equal to 1. Because, yeah. Repeat. Right. So if in a statistical lens, what will you say that I want to sample theta? That's anyways the goal from some pi of theta. You will say, okay, let us expand the space and let us try to draw sample from pi of theta comma m, the joint distribution of theta comma m. Okay, now that's a joint distribution. You now write it down in using the product law. It will give you pi of theta multiplied by pi of m given theta. Now pi of theta will become your this u theta, and that is coming naturally there. And theta given m given theta will become the kinetic energy. That is now not natural, that you have to model now. Okay. And this product form is going to come now when I go take it and substitute it there. Because still for us it is still summation, whereas in that case it is product. So that is going to come because I want to find the probability of EI. How will I do that? I will do Km plus u theta, that is my H, which is E, substitute it there. What will I get if I do that? So let's give some equation number, right? Let's write it EI equal to, this is 1 or this is 2, this is 1, this is 3, this is 4. So I'm going to substitute 3 and 4 into 2 and then 2 into 1. Okay. So what will I get if I do that? I'm substituting 3 and 4 into 2 and then 2 into 1. And I'm taking D equal to 1 to make life easier. So then what am I getting? P of EI, which for all practical purposes is P of theta comma m, because that's what EI is function of, is proportional to pi star of theta multiplied by exponential of minus m square by 2. Let me know if you are getting this or not. You will get this only. So now you see the form, pi of theta, and that second part is basically m given theta, okay, which is independent of theta. Okay. So if I was doing from statistical point of view, I would start from here, and then I will say modeling the second one as exponential. Okay. So now, can you tell me what is the exponential part corresponding to? That is some distribution. Which distribution is it? Which distribution has a square in negative square inside exponential?
Gaussian.
So what is that distribution? Gaussian. What is the mean? Variance. That is a zero mean Gaussian. That's so in the statistical sense, my modeling assumption would be, let us assume probability of m given theta is a zero mean Gaussian. That will now become the assumption. In this case, that assumption is not, that is coming naturally from the kinetic energy. So this is nothing but Gaussian. Okay. So therefore, P of theta given m is equal to 1 by z pi. What is z pi? Can you tell me what is z pi? Simple. Normalizing constant of pi, the pi star. If we integrate out pi star, that will give you z pi. Obviously, z pi we cannot compute, because if we could compute z pi, our life would have been simpler. We cannot compute z pi, I'm just writing it. Okay. Now from here, if I have to calculate probability of theta, what will I do? If I have to compute probability of theta, I will use the product sum law, and that will integrate out normal to 1, and I will get what I want, pi star. Probability of theta will come out to be pi star theta or pi theta, right? If I have to find out m, I will integrate the first term, I will get normal. That you cannot do, obviously you cannot integrate, but if you want, that's what you are going to do. Any questions till now? Because the majority is done actually. Any question? This is clear? So now, remember we want to do sampling, and we want to sample theta. Theta is my sample, theta is my particle. And in the process we have designed something known as the Hamiltonian H, which is the total energy. And now what we want to do is we want samples of theta, which is the position. So now let us forget about sampling for a little while, and someone tells you that there is a system of particles for which I know the Hamiltonian. Okay? How can you give me some theta values? What will you do? APL 100, Lagrangian and Hamiltonian mechanics. Also APL 203, right? There also I think Hamiltonian Lagrangian was covered, the dynamics course. Hamiltonian was covered only in I think APL 100. I don't know if, because it is not covered every time. I taught it when I was teaching. Okay. So anyways, but it's a derivative of Lagrangian. Okay. So in Lagrangian, you have learned about Lagrangian, Euler-Lagrangian equation, right? And what is the Euler-Lagrangian? It gives you the equation of motion. If you solve it, you can get theta. So the bottom line is that theta and m are now physical things. I have assigned physical meaning to those, which is position and momentum. That means they are governed by the law of physics. More importantly, they are particles, so they are governed by the Newtonian mechanics. So I can use the law of Newtonian mechanics to evaluate theta at different locations, different time. So I can write down the equation of motion. In this case, it will be in terms of Hamiltonian, and then solve that equation of motion for different p, and that will give me different theta and different m. Right? The only problem is that for solving it, I will need initial condition. I will need initial condition of theta, initial condition of m. Initial condition of m, how will I get? I will sample from standard Gaussian. It's there, right? So m sample, I will take a sample from standard Gaussian. Theta, I have to take some initial theta. But once I take some initial guess of theta and initial sample of m, that is my initial condition, now I can solve the Hamiltonian equation. And if I solve the Hamiltonian equation at different time, I will get different theta and m. M I don't care about, I will discard m. I will select some, after some time, some theta I will select. And that will become my proposal. Okay? So to obtain particles which is equivalent to samples basically, we note that theta is position, m is momentum, and h is Hamiltonian. Okay, we note these three things which has physical meaning, which means this theta and m, the particles are governed by the Newtonian mechanics. Okay, this means theta is governed, not only theta, actually m also, I mean the part theta here is particles, okay, is governed by Newtonian mechanics. Okay, one question, what is the difference between Newtonian and Eulerian mechanics? Why am I using the term Newtonian and not Eulerian? So Newtonian is for particles, Eulerian is for rigid body. So that's why Eulerian has the Euler's axiom you have read, but you have read Newton's law. So to give little bit more perspective, only for those who have done APL 100, not for others. Dumir follows Eulerian approach. The book by Dumir follows Eulerian approach. The book by Weir and Johnson and Sanghi follows Newtonian approach. Those two books are the ones that we follow in APL 100, and those two are fundamentally coming from different philosophy. Okay. Obviously, you can consider a body to be collection of particles, and then it can use Newtonian, and that way you can show the equivalence. Okay. But Newtonian, because we have particles. So when you apply the mechanics on particles, then it's Newtonian mechanics. Okay. So there is particle cannot rotate, right? I mean, the omega, rotate, but omega thing is not there. Okay. So this means theta is governed by the Newtonian mechanics. And for Hamiltonian, the equation takes the following form: d theta by dt is equal to del H by del M, where M is the momentum, H is function of momentum and theta position, which is equal to, H is equal to K plus U. U is not a function of M, so that derivative will become 0. So only del U, del K, del M. This is the first equation, Hamiltonian equation. The second equation will be derivative with respect to the momentum. So dm by dt is equal to minus del H by del theta is equal to minus del U by del theta. So these are your two equations. Okay. Two equations, theta and M, guess initial value of theta, M sample from standard Gaussian, solve for it, you will get the value of theta and M. M you will discard, theta is what you are interested in, those theta will become your proposer. Okay. So in this case, the proposal is a deterministic proposal, because these equations are deterministic. If I fix M, fix theta, no matter how many times I solve, I will get the same theta at the same t. So this is a deterministic proposal, which is in contrast to random walk, where even if you start from same xt, your steps are like random, so you get, every time you get different things. But here it is deterministic proposal. Okay, that is a major difference. Obviously, ultimately it is not deterministic because M is your sampling. So every time you sample different M, it changes. Okay. Now the question is how to solve this integration. You can use any time integration scheme, but the most popular one is used, and there is some reason for that, which I will tell later, is the leapfrog algorithm. So this is solved using leapfrog algorithm, which is a second order actually. So Euler is first order, Euler integration, leapfrog is second order. So here leapfrog algorithm is used. Leapfrog is a time integration scheme. So generally leapfrog time integration is used. Okay. Why is leapfrog used? Because remember, this is a Hamiltonian system, which means energy is conserved throughout. There is no dissipation of energy because there is no non-conservative forces here or component. So leapfrog is a symplectic integral. Okay. So symplectic time integration scheme are the schemes that conserve the energy. And this symplectic time integration scheme are schemes, there are many, leapfrog is one of them. because they conserve the energy, they give good results when you are integrating over a long period of time. So generally symplectic integral are used in molecular dynamics. That is one place, okay. So symplectic integral, leapfrog is a symplectic integral, which means it conserves the energy. So Hamiltonian is supposed to conserve the energy. And as a result, over long time duration, you will not see much deviation from the actual trajectory, which is not true if you use Rangakutta or if you use Euler. Those are not symplectic, so there is loss of energy. So when you do over long time steps, they deviate. So that's why this is used. And also, if it is not just symplectic, it is also time reversible. So that means from position 1, if in t steps you are going to position 2, if you reverse the time, you can reach the same position. Okay. So this is also time reversible. So leapfrog is symplectic, and so it conserves the energy and also time reversible. And that is one of the main reasons for using it. Okay. So I will not discuss leapfrog, you can read it on your own. Basically, it's a modification of Euler. You will realize it is just a small modification of Euler. Leapfrog is a symplectic time integration scheme. And that makes it more accurate over long time duration, and also it is time reversible. So if you reverse the direction, you can reach the same point from where you started. Okay. So let us summarize what we have discussed till now. We have discussed many concepts, but fundamentally, if you think from an algorithmic point of view, all you need to do is that you need to sample momentum from a standard Gaussian. You need to initialize theta. Then you need to solve this integration using leapfrog. Okay. And you will decide until what time you want to integrate. And the sample you get at the end of that integration is a proposal. Okay. Now what you do with a proposal? What you do with a proposal sample in a metropolis system? You have a sample. What will you do with it? From a proposal. What will you do? Metropolis, accept, reject, right? You will calculate the acceptance ratio. And then you will decide whether to keep that or not, right? So once you have sample from leapfrog, let's write LF, we calculate the acceptance ratio. And I am telling you that we calculate the acceptance ratio following the metropolis algorithm scheme, not the metropolis Hastings. And you will tell me why. So we calculated using A is equal to minimum of 1, pi star, whatever theta you got now, divided by whatever theta you had. Okay. And I am telling you that this is, you can understand, this is the metropolis acceptance ratio. The Hastings part is missing. Why? How? Correct. So what is the proposal here? Proposal is you will go from theta t to theta t plus 1. Theta t is your starting point. How do you go from theta t to theta t plus 1? By solving these two equations. The previous theta t will be your starting point, and by solving these two equations you go. Right? Now going from theta t to theta t plus 1 and theta t plus 1 to theta t, that will be equal because your time integration is time reversible. So as a result, that ratio will become 1 by 1. Remember here proposal is determined, so it's 1 or 0. There is no probability there. Q will either be 1 or 0. Because you are starting from a given theta and you will reach it with either certainty or You will not reach it with certainty. But anyways, you are right. We use the metropolis ratio and not the Hastings part is we remove because it's time reversible. So as a result, going from theta t to theta t plus, if you can go, you can also go in the other way. And that is because of the leapfrog algorithm. Okay. So things will become very difficult if you don't use leapfrog, because then it will be 1 by 0 or 0 by 1, which means there is nothing to accept or everything to accept. Okay, most probably it will be nothing to accept. So that's why leapfrog is very important. It has to be time reversible. Otherwise, you cannot use it. Okay, and done. That is the metropolis as Hamiltonian Monte Carlo. Okay, so let me summarize Hamiltonian Monte Carlo. What will you do algorithm wise? Concept, there are many concepts, but algorithm wise, you will sample M from standard Gaussian, initiate theta. Then you will solve the Hamiltonian equation to get a new theta, which is your proposal. You will either accept it or reject it. And then you will proceed again. So it's the same steps, only Q is changing. But this algorithm is challenging because there are many parameters. For example, until what time should you integrate? You will decide that. What is the time step you will use for time integration? You will decide that. So you can see additional hyperparameters are coming into picture. So that's why that is a challenging part of this. But if you can select those properly, this is better, I will say, than random walk in most cases. Okay. So algorithm, you will take, obviously there are many hyperparameters, I am not writing those. There are many, delta t, capital T, these are all hyperparameters. Okay. So and then what we will do is you will initiate theta naught, theta to be theta naught, and you will sample M from Gaussian 0, 1, get Y or get, let's call it theta tilde, by using leapfrog. Okay. Then calculate A, which is minimum of 1, pi star theta tilde by theta pi star theta. Or let me call it theta t plus 1, theta t. This is theta t. Okay. And then if, okay, obviously we will also sample U. I forgot to mention U from 0, 1. So if U is less than equal to A, theta t plus 1 is equal to theta tilde with acceptance ratio, whatever it is, I am not writing, else theta t plus 1 is equal to theta t. Okay. So this is basically the algorithm. Now to obviously to implement this, you have to write your own code of leapfrog. I am talking about homework 2. So you cannot use some inbuilt one. You have to write your own code called leapfrog, and other is obviously you have to write on your own. Okay. Clear? So to address the hyperparameter issue, there is a modification to Hamiltonian Monte Carlo, which I am not discussing, but if you want, you can read it on your own. That is known as NUTS, NUTS. So that's an improvement over Hamiltonian Monte Carlo. NUTS stands for no U-turn sampling. Okay. So that's a modification where this capital T is selected automatically. Okay. Okay. So I have what? 5-10 minutes. So let us discuss the other part. Sequential Monte Carlo. Any question on this part? If not, we will move on to the sequential Monte Carlo. Okay. Okay. So another algorithm that is often used is sequential Monte Carlo sampling. Okay. Another algorithm that is often used is the sequential Monte Carlo sampling. So what happens is that for multimodal distributions, if the modes are very far apart, and in between if you have zero probability regions, then it becomes very difficult for metropolis testing to capture samples from both the modes. As an example, suppose I have a distribution which is okay. So this is a mixture of Gaussian. But what you will observe is that there is some distance between the two peaks, and in between there is a large region of zero. Correct? Now what will happen if you try to sample from here? Try to think. Suppose I have to start with some initial condition. Let's say my initial condition is here. Okay? That is my theta naught. What will I do next? I will build a proposal, either random walk or I'm talking about classical metropolis testing, so random walk. So with this as mean, I will probably build a Gaussian like this. So where is the next sample you are expecting with this Gaussian? Somewhere where that violet or magenta, violet color is, right? So maybe somewhere here. And that is a very optimistic sample. I will show you why. So next, what will I do? I will build another proposal on with this as center. I will get a sample here, again an optimistic sample, very less probable those samples are. Third, I will build a proposal like this. Now where you get a sample? Extremely optimistic if you are, you can get a sample here. Right? Now build a proposal. Now this area you can never go. So you now will not now start going back. What does it mean? You will always get sample from the mode or from the Gaussian component where you started. You can never reach the other one. Until and unless every now and then you increase sigma square. If you increase sigma square, what will happen? The Gaussian width will change. And then maybe you are lucky enough, you can jump to the other one. But in a high dimensional scenario, you will never know how many of these peaks are there. So naturally, you cannot do that and manipulate that. So these are scenarios where metropolis testing fails, the classical metropolis testing. Right? Sequential Monte Carlo is built to address this kind of scenario. Sequential Monte Carlo actually addresses this kind of problem quite nicely. Okay. So what is the idea, or rather the problem statement? Let's first write. Problem statement is we'll stick to our Bayesian thing. So I have my pi of theta, which is equal to probability of theta given d, which is proportional to probability of theta, probability of d given theta. Right? We know this by now. Nothing new. And the problem statement remains the same. We want to sample from pi theta, even for this kind of scenarios, extreme scenarios as shown above. Okay. So the key idea here is as follows. See if you agree with my observation or not. It is very easy to sample from the prior. You agree? Or do you disagree? It is very easy to sample from P of theta. Is that a correct statement or a wrong statement? P of theta is something you generally assign, and you assign them generally to be some known distribution. It may be complex, but even if it is mixture of Gaussian, let's say, but you know that is mixture of Gaussian. So you can always sample from it directly, even if it is a mixture of Gaussian. You will sample W1 and W2 from some uniform, and then based on threshold, you can select one of those Gaussian, and you can easily sample. So one of the key observation is that P of theta, it is very easy to sample from P of theta. Agreed? So then, can we somehow sample from P of theta and use those samples to represent pi of theta? Understand the problem statement? Obviously, directly you cannot. You can think of importance sampling, you will realize that most of the weights will go to 0 if you try to do that. So it's not easy, but can we? So here is the idea. So the key idea is I will represent pi of theta as P of theta multiplied by P of d given theta, and then I will put a t here, which means this is this to the power gamma t. Okay, and t0 less than t0 or t1, t2, let's say I go it in, I don't know, r steps. Okay, similarly gamma t is also 0, gamma 1, gamma 2, 1. Can you tell me what we have done here? What will happen when gamma equal to 1? When gamma t or gamma t is equal to 1, what will you get? What are you getting? That is the actual distribution from where I want to sample. What I have done is I have created auxiliary distributions. So instead of directly going from prior to something that is very difficult, we'll go through that step by step. We'll take a small step, gamma is equal to 0.400001. Then I'll take 0001. And we'll go in a very small steps from 0, which is the prior, to 1, which is the posterior. And we'll do it in sequential manner. Okay, so the key idea is create auxiliary distributions and then move sequentially. You will move sequentially, right? You will start from the prior, which is easy to sample from. So you already have some initial samples, and then from there you will move sequentially by using metropolis testing, importance sampling, and resampling. These three things are the key. Okay. Or what do you mean? Repeat. Why have we taken power? What if the power is very small? What will happen to the distribution? When the power is 0, what will happen? What will vanish? Prior. If the prior is very small, the power is very small, then also it will be little bit modification over prior. So what we are doing is that we are saying that we will go from prior to posterior, but in small steps. So if I have to draw it, and that is what I was going to do next. So suppose I have this kind of distribution, right? The example that I gave was something like this. Okay. So what will happen is, say my prior is like this. Okay. This corresponds to t equal to 0. When you calculate t equal to 1, t equal to 1, not gamma t equal to 1. Gamma t1 equal to 1 will be the last thing. This is t equal to 1 or t1. You will see that you are getting something like this. When t equal to, let's say, I don't know, t8 or t9, you will probably get something like at the end when t equal to 1, I mean gamma t equal to 1, then you will get this thing. In between, obviously, we will also get this kind of thing. So what you are doing is you are transitioning very slowly from the prior to posterior. So naturally, this low probability region does not arise all of a sudden. You will, and because you are going from previous step, there were samples there, so they will get reinitialized. So you will be able to go from here to there.
So we have to take the prior in such a way that it will absorb.
Correct. So that's why it's sequential, right? That will happen automatically. Because of gamma t, this will happen automatically because it's a combination of prior and like load. Okay, that you don't have to do anything. It will automatically transition from there. Okay, so now you will use these 3 steps sequentially. So what you will do is simple, you will sample from prior and then move the prior using metropolis testing kernel, random walk kernel, and then you will assign importance weight to them and repeat it. So I'm repeating, there are 3 steps. You initialize, draw sample from the prior, then move those samples using metropolis testing that you know already. Then you assign importance weight, which is the previous auxiliary by the next auxiliary. So you'll assign importance weight and then you repeat. The resampling step I am not telling. Resampling step, what will happen is that after some point many of the weights will go to 0. At that stage you have to resample so that again the weights become 1 by n. You don't want weights to go to 0. So that is the resampling step. Okay. So I will share the algorithm. This algorithm I will share separately. But eventually it's basically application of these 3 things. If you have any doubt on this, we can discuss it in some practical class. Okay. Okay, then I'll stop here. Thank you.